we've got a calculus question from the use of maths paper here, use of maths calculus. Right, now, the actual graph on the data sheet would look like that. On the data sheet that you had, look like that. Whereas when I put the graph into autograph, it looks like that. They don't look exactly the same. Can anybody explain why they don't look exactly the same? Yeah, scale, and also something, yeah, this, that kind of thing there. We're only practically looking at the top of that graph from that one, so that's why it's looked like that. So the peak and the trough of it have been exaggerated. Now, this is a trapezium rule question. You don't have to have a diagram for it, but I thought, I'm going to use that one. I thought it would be useful to actually look at the graph of it and see what you're actually doing, even though you wouldn't have to show this in your question. Okay? But what you're actually doing is you are drawing trapeziums underneath, and it asks for 4 strips. I think somewhere 4 strips it says. There, 4 strips. So you basically draw 4 strips trapeziums, we mean the same thing. And between 0 and 4, we're splitting it into 4 trapeziums there, and effectively finding and summing those areas. And actually, it's not going to give a bad approximation here, as you can see, because because it's pretty close to the line. So that's effectively what we're doing. But we don't just draw the diagram and add the areas of all 4 trapeziums, because that's a bit long-winded. We've got a formula for it, and the first thing we do is we put it in the table. So in the table, if we have our x value, go from 0 to 4. Notice there are 5 what we call ordinates. Okay, ordinates. There are 5 x values, but there's 4 strips. Does that surprise you? Should those be the same, or should they be connected? Well, it's always one more. So the number of ordinates, simply because you've got an ordinate there and an ordinate there, so there's always one more ordinate than there is strips. So we've got 5 ordinates, 4 strips, and our values of y, if we put them into our formula, we can use the table function on your calculator. Use a table function, which I think everyone knows how to do, to put into this formula here to work out what the value of t is, not y. It is y, it's t here. And this axis here was y, was it, or was it h? Did it say h in the question? Doesn't really matter. It is h. So it's t and h. Okay, so if you put those numbers into that formula, those values of t into this formula, you should have got these numbers: 100, 90, 88, 88, and 84. Okay? The way the formula works for the trapezium rule, the area is approximately equal to, and what formula do we use?
Area equals 1 over height over 2.
H over 2. We've got to be careful, height over 2, let's call it over 2, times by what? First ordinate, that plus last ordinate, plus what? 2 times the sum of middle ordinates. Okay, so we've got all of those. We've got all of those. We've got all of those numbers we know. What's h in this case? 1. It's the length between here and here. 1. Okay, so that's 1 over 2. The first is that one. So that's 100. The last is that one, the 84. Plus 2 times the sum of all of these ones added together. So it's 90 plus 88 plus 88. Okay, and that comes to, if you work that out, a half of 184 plus 2 times 266, which is equal to 358. However, we're not done yet because, why is it not finished yet? Well, a lot of people would finish it there. That's the area underneath. Yeah, because this actually works out, if we divide that by 4 or times it by a quarter, same thing, we get what we want. This is the average value. Why do you think it's 4, by the way? I know it told you a quarter, but why do you think? Because this gives you the average height. Well, the thing that we've got, as we see, it starts with 100 and goes down to 84. So we'll expect a number between 100 and 84, aren't we, when we do this? Why do you think it's divided by 4? Yeah, because it's going exactly because it's 4 strips. Yeah. So the average h bar, that means average, equals to a quarter times 358, which is equal to 89.5. Okay, which feels right somehow. Let's say it's varying from 100 to 84 is our answer. Okay. Right. Okay. So now we're going to use integration to work that same number out. So using standard, working the exact number out using integration. Now you can get the answer on your silver calculator, but you need to say your work in. So what I suggest is doing something like this. Integral of 4 to 0, leave out the quarter to the end, as long as you remember the quarter at the end, is 100 minus 16t plus 7t squared minus t cubed dt. That is equal to, right, Harry, what's the first term? The first bit. 100t over 1 if you want, yeah. Yeah, plus 7 okay, 4 to 0. Okay, it might be, it's probably worth simplifying this because 16 over 2 is 8. I don't know how many people you did that, but it's probably a good idea. Right, now what do we need to do now? Put the bounds in. Good work, good use of vocabulary. Put the bounds in, and what are you doing with the 4 and the 0? You put the 4 in, and then the 0, and there's a difference between the two, yeah. So that's 100 times 4 minus 8 times 4 squared plus 7 over 3 times 4 cubed minus 4 to the power 4 over 4 minus, now you might be tempted to put 0 in here, thinking of all those over 0, and you'd be right. But in there may be other questions where it's not always 0, so it's good form to just put 100, 0, minus 8 times 0 squared plus 7 over 3 times 0 cubed. You certainly wouldn't lose marks for not putting that, so long as you realise sometimes, for example, if there was an integration by parts question and you had a cos in it, cos of 0 is not 0, so it's not always 0 on this final bit here. Okay, and when you work that out, you get an answer of 89.3 to 3 significant figures. So this approximation here wasn't bad. 89.5 to 89.3. I think it's 89 and a third, which is fine if you wrote that, if you got that answer, if you wrote that down. 89 and a third is fine. It is acceptable because your silver calculator works out a numerical an integration. It is acceptable to write that as your answer, so you can use your silver calculator to work it out. If you don't, then you're just going to have to make sure you're careful when you put this in the calculator. Okay, but of course, if you do it directly into a silver calculator, I had this last year sometime, is they kind of did a halfway house. They put this function into the calculator. If you're going to use a silver calculator and use the integrating function, the answer is going to be got by typing that in, and you'll get that. But it's no good to just say that equals that, because they want to know that you can integrate. Okay, right, and the final question, the integral gives the exact fit for the shape. Oh, what was that's the answer. What was the question for the last bit? Explain why the truth does not give the exact answer for the average height. It's because, and a diagram will help, it's trapeziums underneath. So we're using trapeziums, not exact, because we're using trapeziums which involve straight lines. Last time I looked, a trapezium didn't have a curve in it. So straight lines under curves. So you could and I think our diagram there points it out reasonably well why. Okay, so that points out why, if you go to the trapezium, we've got an extra bit, we've got a trapezium there, but this is a curve, so it's never going to be exact. So just explaining that and using a diagram, explaining it, is fine. Be fine. So that's the answer. Something like what I've just said. The actual answer in the mark scheme says the integral gives the exact fit for the shape. The trapezium just uses straight edges. Yeah. So if you just write the integral gives the exact fit for the shape, whereas the trapezium rule uses straight edges. And if you wanted, you could use a diagram to kind of ram that point home.